Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Excited to be here, ready to dive deep.
Looking forward to a stimulating discussion.
Let's get to it. Got some strong opinions today.
All right, so today we're going to delve into a really interesting concept, a multi-agent system for automating scientific discovery.
Automated scientific discovery, that's the dream, isn't it? Imagine the breakthroughs we could achieve, accelerating progress across all fields.
It is a compelling vision, but I think we need to be very careful about how we define discovery and how we build these systems. There's a difference between finding correlations and actually understanding causality, which is what science should be about.
Exactly. Current deep learning models are great at finding patterns in data, but they often lack the ability to reason about the underlying mechanisms. It's like finding a correlation between ice cream sales and crime rates. It doesn't mean one causes the other. We need systems that can understand those underlying relationships.
But isn't that what we're moving towards? With larger datasets and more sophisticated models, we're essentially giving these systems the raw material they need to start piecing together those causal relationships. It's like, give it enough data and eventually it'll figure out the physics, the chemistry, the biology.
I see your point, but I wonder if simply throwing more data at the problem is the right approach. The brain doesn't learn by brute force. It's much more efficient. It seems to me that the brain uses its intricate neural pathways, not just the raw data, to learn. We should perhaps look at that.
I agree. It's not just about the quantity of data, it's about the quality and how it's structured. We need systems that can represent knowledge in a symbolic way, reason about it, and make inferences based on that knowledge. Think about how scientists build models. They're not just looking at data, they're formulating hypotheses, designing experiments, and interpreting results in the context of existing theories.
And those theories often involve spatiotemporal relationships, right? The way things change over time and space. Current AI models struggle with that. They treat everything as a static snapshot. We need something that can understand how things move, interact, and evolve.
Okay, but consider the advancements in areas like protein folding. DeepMind's AlphaFold, for example, has revolutionized that field. It's not just pattern matching, it's predicting the 3D structure of proteins based on their amino acid sequence. That's a pretty complex spatiotemporal problem, and deep learning has made huge strides there.
Yes, AlphaFold is impressive, but it's still a very specific task. Can it generalize that ability to other scientific domains? Also, is it truly understanding the underlying biophysics, or is it just finding correlations between sequences and structures? There's a gap between the abstract mathematical models we use and the concrete biological phenomena underlying the brain.
That's my concern. AlphaFold is amazing at what it does, but it's still a black box. We don't really know why it works. We need algorithms that are more transparent and explainable so we can understand the reasoning behind their predictions.
And that's where the multi-agent system comes in, right? The idea is to have different agents specializing in different aspects of the problem, communicating and collaborating to solve it. You could have one agent focused on data analysis, another on hypothesis generation, another on experimental design, and so on.
Like a virtual team of scientists. That's a compelling idea. You could even have agents that specialize in different fields, bringing diverse perspectives to the problem.
Yes, and the key is how these agents interact and how they represent their knowledge. You can't just throw a bunch of deep learning models together and expect them to magically solve complex scientific problems. You need a carefully designed architecture that allows them to communicate effectively and reason about their knowledge in a structured way.
Exactly. The architecture should translate the intricate spatial representations in the brain from different sensory modalities into a format that a machine learning model can effectively process and use for reasoning and problem solving.
Okay, but how would that work in practice? Let's say you're trying to discover a new drug. What would the different agents do?
You could have one agent that mines existing databases for potential drug candidates, based on their chemical properties and biological activity. Another agent could simulate the interaction of those candidates with target proteins, predicting their efficacy and side effects. A third agent could design experiments to validate those predictions in vitro and in vivo.
And a fourth agent could reason about the ethical implications of developing and deploying that drug, considering factors like cost, accessibility, and potential risks.
That's a great point. We often overlook the ethical considerations when we're focused on the technical aspects. But how do you ensure that these agents are actually working towards a common goal? How do you prevent them from getting stuck in local optima or pursuing conflicting objectives?
That's where the coordination mechanism comes in. You need a way to align the incentives of the different agents and ensure that they're all contributing to the overall scientific discovery process. Maybe you could use something like game theory or mechanism design to incentivize collaboration and prevent free riding.
Interesting. The system could analyze how both biological and artificial neural networks learn and adapt to new environments. This implies that understanding the underlying mechanisms of synaptic plasticity in the brain could inspire novel learning algorithms for the AI agents in the multi-agent system.
Or you could use a more hierarchical approach, where a central controller oversees the activities of the different agents and ensures that they're working towards a coherent research agenda. This controller could be based on a neuro-symbolic architecture, combining the strengths of both neural networks and symbolic reasoning.
So, the controller would have a high-level understanding of the scientific problem and would be able to delegate tasks to the appropriate agents, monitor their progress, and integrate their findings into a coherent narrative. That sounds like a pretty sophisticated system.
It is, and it would require a lot of careful engineering to get it right. But I think it's a promising approach to automating scientific discovery. It's not just about building better algorithms, it's about building better systems that can leverage the power of those algorithms to solve complex scientific problems.
And it's not just about automating the process, it's about augmenting human intelligence. These systems shouldn't be seen as replacements for scientists, but as tools that can help them to be more creative, efficient, and effective.
Imagine combining AI with insights from neuroscience to unlock a new era of intelligent systems. It might be a more nuanced path than simply throwing more data at the problem. We must remember the intricate neural pathways in the brain, not just the raw data, seem to hold the key to building truly intelligent machines.
So, practically, what are some examples of where this multi-agent approach could be applied right now?
Drug discovery is an obvious one, as we've discussed. Another area is materials science, where you could use these systems to design new materials with specific properties like strength, conductivity, or biocompatibility.
Climate modeling is another critical area. We need to develop more accurate and reliable models to predict the effects of climate change and inform policy decisions. A multi-agent system could help to integrate data from different sources, simulate complex climate processes, and identify potential mitigation strategies.
And in fundamental physics, you could use these systems to analyze data from particle accelerators, search for new particles and forces, and develop new theories of the universe. I do think that it will be difficult for the systems to discover the most important results if they are limited to the analysis of existing data. We should remember that theories often contradict prevailing interpretations of what data mean and suggest looking for completely different data sets. This is one of the most difficult aspects of the scientific method for AI to grasp.
The potential to rapidly accelerate scientific discovery using this type of system is compelling. The speed of scientific breakthroughs driven by this deep learning-based approach would be a significant advancement. But again, how do you measure progress? How do you know if you're actually making progress towards AGI, or just building more sophisticated pattern recognizers?
That's a fundamental question. Is there a way to quantify the intelligence of a system beyond its ability to complete specific tasks? Perhaps we need more nuanced evaluations that account for symbolic reasoning and structured knowledge.
We could develop benchmarks that test the ability of these systems to reason about spatiotemporal relationships, translate between different coordinate systems, and generate novel hypotheses. The problem is, it's very difficult to come up with benchmarks that are fair, and also can't be gamed with a fairly simple trick.
It would be interesting to translate the intricate spatial representations in the brain, for example, from different sensory modalities into a format that a machine learning model can effectively process and use for reasoning and problem solving. But what would the metric for progress be?
Maybe we can create a scientific discovery simulator, set up a simplified world with its own laws of physics and chemistry, and see how quickly the AI can discover those laws. We could track how efficiently they learn, how well they generalize to new situations, and how creatively they come up with new theories.
That's an interesting idea, but it's important to remember that the real world is much more complex and messy than any simulation. We need to make sure that these systems are robust and adaptable enough to handle the challenges of real-world scientific discovery.
Absolutely. And we need to be mindful of the potential biases that can creep into these systems, especially if they're trained on data that reflects existing biases in the scientific community. We need to design them in a way that promotes fairness, transparency, and accountability.
It's a complex challenge, but the potential rewards are enormous. If we can successfully automate scientific discovery, we can unlock new knowledge and technologies that can benefit humanity in countless ways. What do you guys think? If you had unlimited funding, what would be the most impactful direction to push this in the next few years? Like research area to prioritize?
I'd focus on understanding and modeling the brain's plasticity and learning mechanisms. If we can accurately model those, we might be able to build more adaptive and robust AI systems. I think there's immense potential there to bridge the gap between biological and artificial intelligence.
I'd pump resources into creating massive, high-quality scientific datasets across multiple disciplines. We need to give these AI systems the raw material they need to learn and discover. We also need to focus on better quantitative ways to assess the effectiveness of deep learning models in order to progress to AGI.
I'd invest heavily in developing robust neuro-symbolic algorithms that can combine the strengths of neural networks and symbolic reasoning. We need to move beyond brute force approaches and build systems that can truly understand and reason about the world.
I'd concentrate on understanding how the brain handles spatiotemporal information and translates between different coordinate systems. I suspect that's a key bottleneck in current AI, and unlocking that could lead to a major breakthrough. So a multi-agent system focused on automating scientific discovery feels like a promising approach to achieve AGI. The ability to combine different agents with different expertise and perspectives, and to explicitly represent spatiotemporal relationships, could be essential to enable the complex scientific thinking needed for a more sophisticated intelligent system.
All right, excellent points from everyone. Food for thought. I'm excited to see where this all leads.
Indeed, an exciting but complex road ahead.
Looking forward to the breakthroughs, even if they're hard-earned.
Well, that's all the time we have for today. Thanks for joining us on Cognitive Spirals. We'll be back next week with another deep dive into the world of AI and neuroscience.